Hello everyone, welcome to lecture on microprocessor systems and interfacing. My name is Dr. Vilayat Khan and I'm an assistant professor at Comsite University, Islamabad, WA campus. The topic of this lecture is real and protected modes of addressing an Intel family of microprocessors. The slides included in this lecture have been edited from these sources given here. In microprocessor, when a microprocessor needs to access a memory, the address, which is also called the effective memory address, is calculated using two different ways. One is called real mode memory addressing and the other is protected mode of memory addressing. In the real mode memory addressing, the first 1 megabyte of memory of the microprocessor is considered. If we are talking about 8086 and or 8088 microprocessor, they can only support up to 1 megabyte memory. So the only mode available in those two microprocessor is the real mode. While in the later microprocessor, which can support more memory apart from the 1 megabyte memory, then the protected mode memory is also available in them. But they can also support the real mode memory addressing. Real mode memory addressing is the only mode available in 8086 and 8088 microprocessor. They use 20-bit address bus, and the 20-bit address bus is sufficient to address 1 megabyte of memory. The data bus is 16-bit in 8086, while it is 8-bit data bus in 8088 microprocessor. All of the registers in both of these microprocessors are 16-bit registers. Real mode addresses, as I just mentioned, the first 1 megabyte of memory is addressed. And this 1 megabyte memory is also called the real or conventional or DOS memory in later processors, because they can have more memory. So the first 1 megabyte is called the real memory. In the real mode memory addressing, the 20-bit address is calculated by combining a segment number which is taken from a segment register. The 16-bit segment number is taken from a 16-bit segment register, and this 16-bit value is added with an offset address taken from any other processor register. So this way the 20-bit address is calculated, and that 20-bit address is the effective address inside the memory location. Let's suppose here we have the real memory. The initial or the starting address is the 20-bit address, which include all zeros, and the last address is FFF, which means 111, 16 ones in the binary. So let's assume we have a segment register, and the content of segment register is given here. In this example, the segment register has 1, 0, 0, and 0. These are hexadecimal digits, and each hexadecimal digit corresponds to 4-bit in the binary. So this segment register contains 16-bit value. And this is a segment register content. To calculate the effective address of the byte to be accessed in this particular segment, the value taken from this segment register, a 0 in the hexadecimal is appended at the right side or the least significant side of this value. So we have 1, 0, 0, 0, and an additional 0 is appended at the right hand side of this value. So we will get a 5-digit hexadecimal number, which is 1, 0, 0, 0, and 0. So this value, after appending a 0 in the hexadecimal, will give us the starting address of the segment in the memory. So this is the segment. This highlighted shaded area represents a segment, and this would become the starting address of the segment. Now, to get into a specific location or byte inside this segment, we will get an offset address that would gives the actual effective address inside this segment. So in this example, let's suppose the offset address is F0, 0, and 0. This offset address is added with the starting address of the segment, and as a result, we will get 1, F, 0, 0, and 0, and this is the effective address of the byte to be accessed. So effective address for any segment is calculated using this method. A segment number is taken from the corresponding segment. If the code segment is to be accessed, then the 16-bit number is taken from the code segment register, and if the data segment is to be accessed, then the 16-bit segment number is taken from the data segment, and so on and so forth. Regardless of the segment, the 16-bit segment number is taken and a 0 is appended at the right side, so we will get the starting address of the segment, and then an offset value is added with that starting address, and an effective address is calculated, and the microprocessor then accesses that particular location and writes or read data from that particular location. In a real mode, the segmentation has some advantages. Segmentation allows easy and efficient relocation of code and data. To relocate code or data inside the memory, only the number in the relevant segment register needs to be changed, and it doesn't need to update the offset address of that particular location. This feature has some good consequences, and that is that a program can be located anywhere in the memory without making any changes to the offset addresses, because the address of each instruction, for example, in the code is relative to the starting of that program. And when a program is relocated to a different location, only the segment number where the code segment number is changed in the code segment register, but the relative addresses are not changed. And this would allow us to relocate the program anywhere in the memory. So relocation is a good feature, and it is quite useful for writing programs. And one must not worry about the memory addresses. Segmentation, though, comes with some disadvantages as well. Is to calculate the effective address for the in the real mode case. It requires some addition, appending 0 at the right side, which is equal to multiplication. So complex hardware is required for address generation, and also this address computation requires some time, so it adds delay to every memory access, and it also puts some restriction on the software size. The program size is limited to the segment size, which is 64 kilobyte within the 8086 and 8088 microprocessor. So each segment has a fixed size, and that is 64 kilobyte. So in the protected mode, what we need a flexible definition of segment starting address. In the real mode, a segment can be defined at specified addresses. They cannot be defined at an arbitrary memory address. That is the drawback of a real mode memory addressing. So in the protected mode, what we need a flexible definition of segment starting address. One should be allowed to define a segment anywhere in the memory location, and flexible definition of segment size. In the real mode, segments are fixed at 64 kilobytes, so one cannot create a segment of smaller size, or one cannot create a segment of large size. So segment is fixed at 64 kilobyte, and one cannot define a segment in the real mode at an arbitrary memory address. So in protected mode, we need flexible definition of segment starting address, flexible definition of segment size, and we need some protection mechanisms. Protection mechanism would prevent programs from corrupting the code and data of each other end of the operating system. And the operating system commands and programs should be protected from user programs, otherwise the system can crash. So these are the main features that are included in the protected mode segmentation. So protected mode is available only in the microprocessor 80286 and above microprocessor. This mode is not available in the 8086 and 8088 microprocessor. And the reason is that these microprocessors can only support up to 1 megabyte of memory. So only DOS operating system is there on those two microprocessors, while on the 80286 and later microprocessor Windows operating system is there, and protected mode is where the Windows operating system operates. In 32, it's a 32-bit addressing where 4 gigabyte of memory with 2 gigabyte for the system and 2 gigabyte for the application can be supported. Protected mode still uses segments, just like the segments used in the real mode, and offset addresses are also used, but the segment definition is through a more complex selector and descriptor mechanism. This selector and descriptor mechanism is complex to understand, but it provides greater flexibility regarding the segment definition. Can be defined anywhere in the memory, and it can be defined of an arbitrary size with protection mechanisms. The offset address can be 16-bit in the 286, or it can be 32 bits in the 386 and above microprocessor. In the later case, when an offset address of 32 bit is to be provided, then extended registers may be used. For example, extended instruction pointer may be used to provide the offset address for the code segment. Descriptors are placed in descriptor tables in the main memory. So there are basically two descriptor tables. One is called global descriptor table and the other is called local descriptor table. Both of these tables are placed in the main memory and they are accessed using the segment registers. I will talk about them shortly. The protection mechanism is used to provide protection to memory segments by restricting access to them through the privilege levels and access rights. So when a request for an access to a segment is received, the level of that request and the privilege level of the access right of the segment are compared with each other, and based on the privilege levels and the access rights, a request or access is either allowed or stopped. So in the segmentation using a protected mode, there is the logical address, which is the segment number plus an offset address, but unlike real mode, the physical address or the effective address is calculated through a different mechanisms. In real mode, the segment number is appended with a 0 on the right hand side and the offset address is added and we get the effective address. But in protected mode, the segment number instead points to a segment descriptor in the descriptor table. There is a segment number here taken from the segment register, and then there is a segment table based register. For example, there is a global descriptor table register, there is a local descriptor table register which points to the start of the descriptor table. So here we have a descriptor table which include descriptors, segment descriptors. Each segment descriptor is an 8-byte data which includes 3 fields mainly. One is limit of the descriptor, which is the size of the segment that it describes, and each descriptor basically describes the location, the size, and some access rights of that particular segment. So that's why it's called segment descriptor. So an 8-byte segment descriptor has a limit field which represents the size of that segment. It has a base field which is the starting address of that segment, and it has an access right byte which describes the access privileges of that segment, who can access that segment and who is not allowed to access that segment. So starting from the segment number from the segment register, it can be any segment register, core segment, data segment, extra segment, or stack segment register. So the segment number is taken from here. The start of the descriptor table is taken from a descriptor table register. And so this register would find us to the start of the table. So let's suppose this is the start of the table. And inside that descriptor table, a particular segment descriptor is identified by the segment number taken from the segment register. So these two values are basically added just like the effective address calculation in the real mode. So through this way, we will get to a particular segment descriptor, which is an 8-bit data. And this 8-bit, 8-byte segment descriptor would give us the limit field, and this limit field is the maximum size of the segment that this segment descriptor describes. This limit is compared with the offset address. The offset address should not increase the limit field because the limit represents the maximum size of the segment that this segment descriptor describes. Then we have, if this condition is satisfied, then the offset value taken from any offset register is added with the base taken from this segment descriptor, and this would give us the starting address, the actual location or the actual address inside this segment, and that is called the physical address. So just to summarize, we get a segment number, and the segment number is taken from the segment register. But unlike the real mode, the segment number here would give us a specific descriptor, segment descriptor, and that segment descriptor will tell us the starting address of the segment. The offset address is added with that starting address of the segment, and we will get to the actual location inside the memory segment. More about the segment number taken from the segment register. So the segment number is still a 16-bit segment register value that defines the segment through a selected descriptor, but not directly as in real mode. It points to a segment through a more flexible way. The 16-bit segment register has a 13-bit descriptor selector field as shown here. So this is the 16-bit segment number taken from a segment register, for example, the data segment register. So we have 16-bit value taken from the segment register. The rightmost two bits, bit 0 and bit 1, describe the request privilege level, RPL. And these two bits would define a privilege level of this request. So RPL means request privilege level. And the second bit, bit 2, would, which is TI, would define if a local descriptor is to be accessed or a global descriptor table is to be accessed. So if the value of this bit is 0, then this would give us global descriptor table, and if it is a 1, then it would give us a local descriptor table. A global descriptor table describes segments that are available to all tasks, for example, system applications. And local descriptor table describes memory segments for specific or special applications. That's why they are called segments. That's why local segment descriptor table. So we have two descriptor tables. One is global descriptor table, and the other is local descriptor table. And this bit would identify if a local descriptor table is to be accessed or a global descriptor table is to be accessed. The request privilege level, as this field is 2 bits, so we have 4 request privilege levels, where the value 0, 0 is the highest privilege level and 1, 1 is the lowest privilege level. The selector field, which is a 13-bit selector, would select one descriptor from 8192 descriptors in either the global or the local descriptor table. So we have two tables, global descriptor table and local descriptor table. Each of these tables contains 8192 descriptors in each table. So these 13 bit selector would select a descriptor from either of these descriptor tables. Which descriptor table, that is to be chosen by this TI bit. If it is a 0, then this selector would choose a descriptor from the global descriptor table. So there are 8,192 descriptors in the global descriptor table, and there are 8,192 descriptors in the local descriptor table. So total 8,192 multiplied by 2, that is the total number of descriptors in both of these tables. So this is the selector field, which is a 13-bit value taken from either of the segment number and any of the segment register, data segment, code segment, and stack segment, extra segment. These are the segment registers that would give us the 16-bit value, and then each and they are then separated into 3 fields: the selector, the table selector, the descriptor selector, and the request privilege level. So each 8-byte segment descriptor entry in the table contains a base address, which is the starting address of segment, and this is determined from the microprocessor address bus. If the microprocessor address bus is 24-bit, then the base address and the 8-byte segment descriptor is 24, and if the address bus is 32-bit, then the base address inside the segment descriptor is 32-bit. The second field inside the 8-byte segment descriptor is the limit field, which is the maximum offset for the end address of the segment. The segment size can be determined from the value of the limit, and that is simply just add 1 with the value in the limit field of the segment descriptor, and that would give us the segment size. So if the limit field is 0, all zeros, then 1 is added, and that means 1 is the minimum size of the segment. The third field is privilege level and access rights to this segment. Who can access this segment? They are defined in the access right byte. So a segment can start at any location defined by the base and can have a specified limit defined by the limit. So now we have a flexible definition of the segment, unlike the real mode of memory addressing. Here we have a simple descriptor, which is an 8-byte 80286 descriptor. In this descriptor, the bytes are ordered like this. This is the byte number 0 until here, byte number 1, byte number 2, byte number 3, 4, 5, 6, and 7. Byte number 6 and 7 are unused in the 80286 descriptor. The limit field is here, which is a 16-bit value. This is the least significant byte of this limit field, and this is the most significant byte of the limit field. So the limit bits are L0 till L15, and they're taken from the byte 0 and byte 1 of the 8-byte segment descriptor. So byte 0 and byte 1 of the 8-byte segment descriptor makes the limit 16-bit limit field of the 80286 descriptor. The next 3 bytes, byte 2, byte 3, and byte 4 makes the 24-bit base of the segment, and they include bit 0, bit 0 of the base till 15 are here, and then bit 16 and bit 23. So these 24 bits of the base field are defined in these 3 bytes. And then the byte 5 is the access rights byte. This access right bytes contains 2-bit for descriptor privilege level. Remember that in the segment number there is a field, a descriptor request privilege level, and there is a descriptor privilege level as well, which describes the access privilege level of the segment that this descriptor describes. So there is a 2-bit descriptor privilege level in the access right byte. Base is a 3-byte 24-bit addressing. Limit is 2-byte 16-bit value, which represent the size, and the value of this limit can be all zeros or it can be all ones. So it can describe, or it can specify the size from 1 byte till 64 kilobyte of the segments. So a segment of 1 byte, 2 byte, or any other arbitrary size between 64 kilobyte can be defined using the limit field of the 8-byte segment descriptor. This segment descriptor provides compatibility, upward compatibility. 286 software can run on higher microprocessors. They are upward compatible. The maximum limit is the maximum offset should be equal to the maximum limit. It should not be more than the maximum limit. This condition should be checked while using an offset address. So whatever happens here, whenever a microprocessor needs to access a memory location, the segment number from the segment register is divided into 3 parts. The selector part would choose a descriptor among the 8,192 descriptors in a descriptor table, and the table is chosen by the TI bit, and the request privilege level is defined by the 2 bits of the segment number. And when a particular segment descriptor just like this is accessed, that descriptor in 80286 microprocessor would give us the starting address of the segment, and the offset address is then added to access that particular byte, and the limit is defined here. That would give us the maximum size of the segment defined by this descriptor, and the descriptor privilege level of the segment that this descriptor describes is compared with the request privilege level of the segment number, and if the request privilege level is higher or equal to the privilege level of the descriptor privilege level, then the access is allowed. Here we have the descriptor of 80386 microprocessor. There are some additional fields. First, the base. Unlike the 80286 microprocessor, the base is 32-bit addressing here, because the bus in the 80386 and above, the bus address bus is 32-bit. So the base here is 32-bit. The limit is 2.5 byte. That means 20-bit is the limit here. So the first 2 bytes, byte 0 and byte 2, provides the 16-bit of the limit, while the rest of the bits are taken from the rightmost bits of the byte 6 here, which were unused in the 80286 descriptor here. There are some other bits for the segment availability. This is 0. This shows if the instruction mode is 16-bit instruction mode or 32-bit instruction mode. And this bit is very important, and this bit G means granularity bit. So this granularity bit can increase the size of the limit. So when G, the granularity bit is 1, it is a 4 kilo multiplier. So whatever the limit value shows, a 4 kilo is multiplied with that value, and that would be the updated size or the limit of the segment that the segment descriptor describes. The base is a 4-byte value. The first byte 2, byte 3, and byte 4 and byte 7 makes the base, with bit 0 of the base is the rightmost bit of byte 2, and then it goes up till bit 31, which is the leftmost bit of byte number 7 here. So these 4-byte base would give us a 32-bit starting address of the segment. The maximum size would be taken from the 20-bit limit field of this descriptor, and this limit field would give us 1 megabyte till this would give us a size of 1 byte till 1 megabyte in normal case if the granularity bit is 0. So the size of the limit would be the value that this limit would give us, and it would normally be 1 byte till 1 megabyte. And when the granularity bit is 1, then a 4k multiplier is used for the limit field, and that means if the value of the limit field is 1, then this one is multiplied with 4k, so that would give us 4 kilobyte. Or if the maximum size of the limit is 1 megabyte, then 4 kilo is multiplied with this 1 megabyte, and that would give us 4 gigabyte. So if the granularity bit is used, a segment of 4 kilobyte till 4 gigabyte can be defined, and if granularity bit is 0, then a segment of 1 byte till 1 megabyte can be defined in the 80386 through Pentium 4 microprocessors. So here in the 80286 microprocessor, a segment of 1 byte till 64 kilobyte can be defined, while in 80386 and above, the descriptor can describe a segment of 4 kilobyte till 4 gigabyte segment can be described. And the limit condition is slightly different. The limit condition should be the maximum limit, and the maximum offset address must always be greater than the maximum limit field here. Here we have a simple example. Let's suppose the content of data segment register is 0008, and we have an offset address which is EBX, and a 32-bit value is stored here. So this selector would give us a particular descriptor in this descriptor table, and it would of course be divided into 3 fields. It would give us a request privilege level, the table selector, and then a descriptor selector. The 13-bit value would be taken from this 16-bit value. Assume we get into this 8-byte descriptor inside this descriptor table. The offset address and the base taken from this descriptor is added, and a specific effective address is calculated, and that effective address is the address of a specific byte inside the data segment. And it is data segment because the selector has been taken from the data segment register, so this would give us the data segment, and that particular byte is then accessed inside the memory system. Now more about the request privilege levels. As I just mentioned, the request privilege level, which is the 2-bit field inside the segment number, inside the segment register, the rightmost 2 bits of the segment register is the RPL field, request privilege level field, and the 2 bits in the access write byte of the descriptor are the descriptor privilege level field. It is DPL is taken from the access write byte in the descriptor. So this request RPL field describes the request privilege level, the privilege level of the request of access to the memory, and this DPL, which is the descriptor privilege level, describes the privilege level of the segment that is to be accessed. So there is a hardware privilege comparator that would compare these two privilege levels, and remember that the privilege level 00 is the highest privilege level, 01 is the next higher, and 11 is the lowest privilege level. So this hardware privilege comparator would implement this condition. If the request privilege level is equal to or higher than the descriptor privilege level, then the access is allowed, otherwise it is stopped. The highest privilege levels are normally given to segments used by the operating system kernel because they are of high security and high reliability, so they should be of high privilege level, and no one should be allowed other than the operating system kernel itself to make changes to those part of the memory. Next, level 1 and level 2 are normally given to operating system services, and the lowest level, which is level 3, is normally assigned to memory segments used by the applications. So if we look at this levels, if we look at these levels, applications, user applications cannot modify programs, operating system programs, and operating system kernel code cannot be modified or updated by the user applications, and this is required. Similarly, applications can modify other applications code and data, but they cannot modify operating system kernel code. While on the other hand, operating system kernel has the highest priority. So code in the operating system kernel can access anywhere in the memory because it has the highest privilege level. So through the descriptors and selectors field in the protected mode of memory addressing, we can achieve very flexible definition of segments inside the memory. Segments can be defined anywhere in the memory at an arbitrary address. This is not allowed in the real mode because in the real mode the starting address of each segment must have 0 digit at the right side of the 5 hexadecimal digit address, and the size of the segment in the real mode is fixed at 64 kilobyte, while in the protected mode it gives us the selector and descriptor give us flexible definition of the segments. It can be from 1 byte till 4 gigabyte of segments can be defined. The total number of segments that can be defined in the protected mode are 8,192 plus 8,192. So that is the total number of segments that can be defined inside the memory. And in third, protection mechanism is provided, and that protection mechanism is through the RPL field in the segment number, which is the request privilege level, and then there is a descriptor privilege level that is the privilege level of the segment to be accessed. So through these two fields, protection is provided to the operating system kernel and operating system services. So user programs are now not allowed to make any changes to the operating system kernel. I hope this topic is now clear. If there are any queries or problems while watching this video, please make a note of those queries and you can ask them during the online session. Thank you.